Hello students, welcome to the course Verilog HDL. So in the previous videos, we seen some of the examples. Okay. So now in this video, we'll look at the exercises on data flow modeling. Okay. So we'll be introducing some new designs here. Okay. So the Boolean expression will be given. So you have to write the corresponding operators in data flow modeling, and you have to write the Verilog description, stimulus module, and you have to check the simulation output. Okay. So I have three such designs here, so that I try to do here. So before that, what we have learned so far in data flow modeling in the last 6 to 8 videos, so that we try to summarize first, and then we'll look at the exercises. Okay. So first we have taken continuous assignment is one of the main construct used in data flow modeling. Okay. The keyword is assign. A continuous assignment is always active, and the assignment expression is evaluated as soon as one of the right hand side variables changes its value. Okay. The left hand side of a continuous assignment must be a net always, and any logic function can be realized with continuous assignments. The keyword is assign. Okay. Then how to specify the delays we have seen. So delay values control the time between the change in a right hand side variable and when the new value is assigned to the left hand side. Okay. So in an expression you have right hand side. So it will compute at the 0 time maybe, but the assignment will happen at a delay. Okay. So that is the part of delay value specification, and delays on a net can be defined in the assign statement. Okay. So as we have learned three types of assign statement, same way we can use the delay in the regular assign statement, implicit continuous assignment statement, or net declaration. Okay. So this is the idea you have seen in the first part. So then we have introduced the expressions. So assignment statements contain expressions, operators, and operands. Okay, that we have introduced, and various operator types in details we have gone through. Okay, the operator types are arithmetic, logical operators, relational operators, equality operators, bitwise operators, reduction operators, shift operators, concatenation operators, replication, and conditional. So this is a very big class of operators we have in data flow modeling. So this knowledge is necessary for modeling any circuit at data flow level. Okay. So in the operator types, again we have the classification like unary, binary, and ternary, and multiple operators. Okay. So unary operators require one operand, and binary operators require two operands, and the ternary require three operands. Okay. So the concatenation operator can take any number of operands. So this is about with the number of operands. So we will have the classification of operators. And then we have seen a conditional operator at the end, so which behaves like a multiplexer in hardware, or like the if then else. Okay, so this is a behavioral statement, so it will act as if else statement, or as a multiplexer in hardware statement in programming languages. Okay, so this is the with examples we have seen, and we also have seen 4:1 multiplexer design using 3:1 marks, and we have used the nested conditional operators also. Okay, and finally we have designed some examples. Data flow description of a circuit is more concise than a gate level description. Okay, so that is the observation you have made here. So gate level you used to write the detailed logic diagram, and then each of the gates you used to call in the design. Okay, so whereas here you will write a single assign statement, so it is going to be a concise one. Okay, that is the observation you have made. The fourth one, multiplexer and the 4-bit full adder, we have discussed in the gate level modeling unit. So can also be designed by use of data flow statements. So that is what the first two examples we have taken here, and the two data flow implementation for both circuits were discussed. That is 4:1 multiplexer using data equations as well as conditional operator. Similarly, 4-bit full adder using logic equations as well as a carry look ahead adder. So both type of methods we have seen in both the circuits. Okay, and finally a new example, the 4-bit ripple counter is designed using negative edge trigger D flip-flops we have designed. Okay, so this is what we have gone through so far in the data flow modeling. So with this knowledge, so we'll now try to see one by one exercises in this data flow modeling. Okay, the first exercise, Note down, it is about full subtractor. Okay, so as you had full adder, so it is the full subtractor. Okay, so just we'll try to look at the question, what is they have asked and what we have to do. Okay, a full subtractor has three 1-bit inputs x, y, and z. So as it is in full adder, so it is also having three inputs, so named as x, y, and z. Okay, and two 1-bit outputs, difference and borrow. So in adder you have sum and carry, in subtractor you have the difference and borrow. The logic equations for D and B are as follows. So you no need to do any work, so the expression only they have given: x bar y bar z plus x y z bar, x y bar z bar plus x y z, and b equal to x bar y plus x bar z plus y z. Okay, so this is what you are going to get. So write the full Verilog description for the full subtractor module, including IO ports. Instantiate the subtractor inside a stimulus block and test all the 8 possible combinations of XYZ given in the following truth table. Even the truth table also they have given. In the next slide, we will see that. Okay, so this is the truth table. Okay, so question is given now. So now before we write the program, so program is very simple. Okay, so program you can write, I told you, understanding the design is very important. Program is then nothing. Okay, so here subtractor, I will tell you the answer. So just expression is given, just wherever multiplication is there use and, wherever complement is there use the negation bitwise, and wherever plus is there use the or symbol. Your expression is ready, right? And then list of ports you have xyz and db. So input are xyz, output is db. Over. So your program is within 5 to 6 line, it is over. But my understanding here is, in exam this exercise may not be asked like this. They tell you to design a full subtractor straight away, so then you need to know how this expression has come. Okay, so that part I try to explain here. So as I told you, in any example, I don't do for you to by heart any programs. Okay, my intention is to you learn writing the program. Okay, so what is the first step? It is the logic symbol or IO diagram. Okay, so IO diagram for full subtractor, you can call full subtractor. In short, I will write here FS. Okay, so it is a full subtractor. So the three inputs are, it is given in truth table, it is visible. Okay, but we will not write truth table first. Always we are write the design. Full subtractor means it will have three inputs xyz and two outputs, difference and borrow. Okay, so you can note down this how it has come. Okay, so xyz, d is difference and b is borrow. Okay, so these are the two outputs. So this is the first step. Okay, so once you have understood this, so you can write the input combination now xyz. So it starts from 000 to 111. Okay, see here all the 8 combinations are written: 001, 010, 011, 100, 101, 110, 111. So now how these borrow and difference output will come? So for this you should know the rules of Boolean subtraction. Okay, so always you have the 4 combinations. Okay, so 0 minus 0, so we'll have only 4 combinations. So 0 minus 0. Next you have sorry, just a minute, I will take this combination at the end. So next I will consider 1 minus 0. Next I will consider 1 minus 1. Okay, the third rule. And finally I have the last rule. Okay, that is 0 minus 1. Okay, the first three is very simple, you can straight away tell. Okay, so what is the case here? 0, and there is no borrow taken, that's why it is 0. That's why this first one is d, difference, and the this one is borrow. Okay, no need of borrow in the case of this. Then 1 minus 0, it is 1 with the difference borrow 0. 1 minus 1, difference is 0, borrow is also 0. Whereas in the case of 0 minus 1, this is a smaller number, this is a larger number, so you should always take a borrow. That's why you will have a borrow 1, and 0 minus 1 is 1, so 1 1 you will get. So if you know this rule, you can fill this truth table very easily. Okay, hope you have gone through this already, but just to recall, I have done this. Okay, So now we'll apply this. So always start from 0 minus 0 0, 0 minus 0 0, both are 0. Next, see here, 0 minus 0 is 0. First these two will be subtracted, then the result will be subtracted by 1. So 0 minus 1, so this rule will apply. That's why both became 1 1. See here, next again 0 minus 1 will come 1 1, then 1 minus 0 1. So difference is 1, borrow is also 1 in this case. Okay, next 0 1 1. So see here, 0 minus 1 is actually 1, right? So borrow is 1, difference is 1, then this 1 is subtracted, that's why difference came 0. In this truth table difference is written right, okay, borrow is written this side, careful. Okay, so difference is 0, borrow is 1, because here borrow is generated, this is as it is there, so that will be there here. Okay, next 1 0 0, this is the simple one. So 1 minus 0 is 1 with a borrow 0, then 1 minus 0, so you'll get difference as 1, borrow is 0. Next 1 0 1, so 1 minus 0 is 1 with borrow 0. Okay, that's why borrow is 0, then 1 minus 1, it will come difference also 0. Okay, so it is exactly opposite combination you will get for compared to full adder. Okay, for that you should know this rule, then it is very good. So 1 1 0, you have 1 minus 1 0 0, so again 0 subtraction, that's why both are 0. Okay, so no much logic. So see here, this is the interesting combination. So 1 minus 1, it is 0. First subtraction will give 0, borrow is also 0. Next you have 1, so it is comes the 0 minus 1 case now. That's why both the difference as well as borrow becomes 1 as per this rule. Okay, so this is the truth table, hope you have understood. Okay, so just you can pause and note down whatever I have done now. These rules you note down, this in IO diagram you note down, and this truth table you write down. Okay, so now having this, so with the truth table, so now I will try to show you the how expression has come, how it will come. So normally it is using k map, right? So we'll have a two k maps for one difference and one borrow. Okay, so hope you are noting down. Okay, so difference and borrow. So this is a new design, that's why I told you. So this side I will have one variable, I will consider x. You can take anyway. Okay, you can take vertical k map also, you will not get the different result, same. So one variable I have two combinations 0 1. So here I will have 0 0 0 1, and this is 1 1, and then 1 0. Okay, so you know this idea of k map, right? Fine, so now we'll fill this first second column, that is whatever is there for difference, so that we will fill out here accordingly. Okay, so 0 0 0, you have the difference 0. 0 0 1, you have the difference 1. Next 0 1 0, 0 1 0, you have 1. 0 1 0, where it will come here. Okay, so this is 1. Next 0 1 1, the difference is 0. Okay, so this is filled later. Okay, then 1 0 0, you have the difference 1. Next 1 0 1, difference is 0. 1 1 0, again difference is 0. This is the 1 1 0. Okay, and then 1 1 1, the difference is 1. Okay, so by looking at the k map, so you'll come to the conclusion that you could not group any of the bits, so it is a individual bits, right? So this is the individual bits. So now if you write the expression for this, so it will be the expression for the D output or the difference output. Okay, so D is equal to, so write the first one, this is 0 and this is 0 and this is 1. So 0 means in sum of products form complement, so that's why it is x bar y bar z. Okay, x bar y bar z plus, so next one I have here 0 1 0. Okay, so it is x bar y z bar. Okay, x bar y z bar. Okay, clear? Then this you have 1 0 0, that means x is 1 as it is and y in z complement, so y bar z bar plus, then this one you have 1 1 1, nothing but x y z. Okay, so this can be simplified further using same as in full adder, but this is the expression they have given. Just you can check if you have noted down the question. So instead of bar, you have the prime. Okay, so that also can be used. Okay, x prime y prime z, x prime y z prime, x y prime z prime, x y z. This is the expression you have, just you can verify. Okay, so just I am telling you how the design is coming. Okay, so if they ask in exam, so they won't give such a brief question like expression and all. Design a full subtractor, write a Verilog description and stimulus module, they will say. Okay, so that time you should able to write this. That's why I am explaining this part. Okay, so design is more important compared to anything. Okay, so hope this is clear. So note down this. So I will erase this and I will show you similar way the borrow truth table. Okay, so borrow k map. Clear? So just you can pause and note down. So I will erase it. Okay, so now we have to write the again one more truth table, sorry, k map for borrow now. Okay, the same way we'll have the, so if you want to show you vertical one, that also I will show you. Okay, so vertical one I will show you. Okay, so that you should not confuse with, if you are following anyone, so you follow that. Okay, so this side I have two now, that's why x and y I will consider, and this side I have one, I will consider z. Okay, so this is 0 1. Okay, so this is 0 0 0 1, this is 1 1, and this is 1 0. Okay, fine. So now we will fill this table. Okay, so b column we will try to fill with the corresponding input combinations. Okay, so what is 0 0 0? It is 0. Next 0 0 1, it is 1. Next 0 1 0, so where you are getting here 1. Next 0 1 1, again you are getting 1. So 0 1 1, where you are getting here. Okay, next 1 0 0, you are getting 0. So where you are getting 1 0 0, this combination. Okay, 1 0 0, you are getting 0. Next 1 0 1, you are getting again 0. This is this combination. Next 1 1 0, also 0. 1 1 0 also 0, and 1 1 1, you are getting 1. See here, just a difference, just to show you. Like this also you can write the k map. I am showing this in this example. You can write horizontal also. So now if you group this, so you have one combination here, you have another combination here, and you have another combination here. That means you have the three values. So just write the expression now. Okay, borrow is equal to, so first I will write this one. Okay, first this one 0 1 0 1, here 0 1 is there, so here 0 1, that means it is, so this 0 1 cancel out, right? Z bar equal to 1 in, see this one. So that's why this combination will give you result x bar. Okay, so I will write this only, x bar y plus, then this one I will write. So this one means here this y will be cancelled out, x will have the bar, that's why x bar, and you have here z, one you have, that's why z. So this also you have z, but now this x will cancel out, so you'll have yz plus yz. Okay, so the expression what they have given, just to verify, so you'll have the same thing, x bar y plus yz plus x bar z, maybe anyway it will be, so the answer is the same. Okay, so this is the idea to show you how we design our own full subtractor. Okay, hope it is clear. So note down this. Okay, borrow truth table, even you can draw the horizontal k map and you can write, so you'll get the answer same. Okay, just to show you how we will write vertical k map, I have shown in this example. Okay, so in this exercise they have just asked you the program, stimulus module and the output. Okay, but I have shown you because this is the same question. If they ask design, so you should not by heart the expression. Okay, so you have to write the IO diagram first, then truth table you have to write by using the rules of Boolean subtraction, and then you write the k map, write the expression for D and B. So this is the design part. Okay, for design part also they will keep the marks. Okay, so be careful. So design you have to do, simply you should not by hearted programs, you should not write. Okay, so finally, so we will write the Verilog description for this expression. Okay, so that is the next part. So see here, as I told you, the This one is only 6 lines, right? The code is only 6 lines here. Module, output, input, assign, 2 assigns are there, and end module, 6-line code. But understanding this, how this came, it is very important. If you miss one of the parameter here, one negation or one or, so your result is going to be completely changed. Okay, so understand this. Lab programs are there, so lab will practice it. Okay, so as it open, so we'll see. Okay, so before that, we'll try to finish off all this programming part. Okay, so module name I have given fs full subtractor. Then inputs and outputs I have written as list of ports xyz db. Then in that output is d comma b, so that's why output is declared, and input is xyz. Expression is we have done, so just assign statements are used. You can use two assign if you use the semicolon at the end, but comma is used, that's why one assign, both statements are written. So what is meant by D? You had x bar, y bar, z, right? So that is not of x and not of y and z. So this is the bitwise negation, bitwise and, right? And this is the logical or they have used. Okay. So it is not going to be any problem. Okay. Because the result is non-zero or zero. So here in this case, so this nor or this or does not have any much difference. Okay. Fine. So this or they have used, you can use the single or also. Okay. Then not of x and y and not of z. Okay. So the second expression you had x bar, y, z bar. So that is written here. Then x, y bar, z bar was there. So that is written like this. And then x, y, z. See here. Okay. Then with respect to borrow, you had x bar y, x bar z, and yz. Same as. Okay. So if you write the K-map, you are not going to be wrong, right? Simple, right? So just with the operators we have replaced. So this is becomes now data flow description. Finally, our end module. Hope it is clear. So nothing much to do. If you have done this expression part clearly, so this is not a big issue. Okay, fine. So now we'll see the stimulus module for this. The stimulus module is always almost same as full adder. Whatever you have done full adders, because it was having three combinations there, ABC, right? Similarly, we have here XYZ 0002 111 combinations. Okay, so the same way we'll try to write it. Okay, stimulus module. So module test, module name is test. There is no list of ports or port declarations. Okay, the inputs are declared as register, which will hold value XYZ, and outputs are declared as drivers B, YRB, DB. Okay, then we have instantiated the design full adder in this stimulus module with the instance name S1, and then connecting ports by name is used here. That's why dot x of x, dot y of y, dot z of z. You can write it in order also. Okay, just to show you an example, it is again written like this. You can use either way. Okay. Then initial statement is written to monitor the final output $time x y b xyz, and d and b are noted down. Okay, so that is how written. Next we have to just pass the values of the truth table 0002 111. So begin, so initially we have taken 000 combination. See here. Okay, so this is the last bit you have to observe. So 000. Next, with a delay time of 10 time units, so you have changed the combination 001. Next, again with a delay of 10 equal time minutes, so it is 010 now. Next you have 0 1 1, and then finally you have 1 0 0 1 0 1. Okay, so this is how it is written, and then 1 1 0. Nowhere you should miss, right? All the 8 combinations are included here. 1 1 1. Okay, so this is the stimulus module. So end this initial begin. So since here initial is only one statement, begin and end is not written. Okay, so see this observation here, initial just written. So if you have single statement, no need to write here. Multiple statements are there, that's why begin and end is necessary. Okay, so finally end the stimulus module. Okay, so this is the program. Hope it is understood to you. Okay, so now just the output we have to write down in this monitor pattern: 0 10 20 30 40 50 60 70. Okay, so what will happen to the output? So it is from the truth table. Okay, you have to verify from the truth table. Okay, so from the truth table only we started our design. Now finally you have to verify our truth table, our design, whatever we have written in Verilog HDL, because earlier we used to do using breadboards, we told. Now we can do using this programming. The programming will dumped into a hardware, right? So that hardware will now work as full subtractor. So see this, the strength of programming. Okay. So fine. Hope you have understood this. Clear. So now just verify the outputs. Okay. If any mistakes is there, you have to check the designs. Okay. Because in programming, I told you there are two types of error. One is syntax error, another is semantic error. Syntax error will be come to know by compiler. Okay. That means the mistakes of programming, like when you are writing, if you missed one A. Okay. So grammatical mistakes will be told by the compiler, that is called as syntax error. Whereas semantic error, okay, the programming construct everything you have written properly, but you have designed a full subtractor, but it is now giving the results of full adder. If you miss some of the not there, x bar, y bar, z, something we have written, if it is changed to full adder design, syntax error will not give, but semantic error you will not have a design of full subtractor. That's why semantic error also more important. That's why this test bench is written and the output is verified. Okay, fine. So here it is a simple design. That's why 8 combinations you have. Really you will have more combinations in the next examples and all. We'll see there will be more complex combinations. Then in that case we will go for only few combinations. See here. So truth table you verify 000, you had 00, then 001. See the truth table, just verify the truth table, or if you know the rules of binary subtraction also you can verify. Next 010 also 011, then 011 it is 01. Here see in truth table we have written difference here and borrow here. Okay, but here difference we have written first, borrow next. Okay, don't confuse there again with the truth table. Okay, so that's why rules you should be strong. 100 means difference is 1, borrow is 0. So 101 it is 00. 110 also you will get 00. 111 you have the difference, borrow 1. Okay. So if you write here to here something mistaken, so then change will happen. Okay. So this is the idea of showing you the design of full subtractor, one of the thing. Okay, but in real time, in real circuits we are not going to design full subtractor. Why? Because the full, there is no functionality like subtractor in digital circuits, because the negative numbers we are writing in one's complement form. That means the subtraction also we will do using addition. That's what you have learned, no, in module 3 in the basic electronics, right? So subtraction using addition. So you have taken the second operand complement, then you have added it, and if there is a carry, so you have discarded it, or either you have added to the least significant bit. Recall these concepts. Okay, so that's why full subtractor, just to show you, you can design as like any others we have shown, but normally the subtraction will not be done, so it is done using addition. Okay, that's why it is kept in exercise, just to have a grip on your operators. Okay, hope it is clear. So this is about full subtractor. So in the next video we'll try to show you a magnitude comparator, and then counter is there. Okay, so we'll see how much time it will take. So for today we'll end the session here, and in the next video we'll look at the other exercises. Okay, so go through once again, note down, and if any doubts is there, note down. Okay, thank you. We'll see in the next video.